Hello again. So now that we know more about where functions are increasing and decreasing and some of the notation associated with that, let's look at some situations that lead to an interesting result. Alright, suppose that we have some function and we know that the derivative of the function is less than 0 on negative infinity to 4. The derivative at 4 is 0, and the derivative is greater than 0 on 4 to infinity. I want you to try and pause for a moment. Draw a curve that meets these conditions. All right, so this is fairly straightforward. What is this saying? F, since the derivative is negative, f is decreasing on negative infinity to 4. F prime at 4 is 0. That's a critical number, right? We have a critical number at 4. And then f prime at is positive on 4 to infinity. Then the function is increasing. So all you needed to do was draw a graph. And here's 4. And it's decreasing when x is less than 4, then stationary, and then increasing. There is a function where f prime of x is negative on negative infinity to 4, 0 at 4, the derivative is 0 at 4, and then the derivative is positive when x is greater than 4. What happens at 4? Let's notice something. What's special at 4? What could we call that point? Well, if you remember what we talked about in an earlier topic, what we can see is there is a minimum. It's at least a relative minimum. We see that there is a minimum value at x equals 4. Now, we can't really say, is it an absolute? We don't know that for sure, but it's at least a relative minimum. All right, look at the next one. Now, the derivative is positive on negative infinity to 4, then 0 at 4, then negative on 4 to infinity. So if we were to draw this function, and again, here's 4, the function would have to be increasing, stationary, then decreasing. And if we look at this one, this graph, now we see that we have a maximum value. At x equals 4. All right, what about this third situation? Now suppose that the derivative is positive, 0, then positive again. If we were to draw a graph for this, here's 4. So I would have to draw a graph that's increasing. Draw a graph that's increasing, and it flattens here. Oops. It flattens at 4, but then it increases again. Now if we look at what happens there at 4, is there anything special about that point? Is it a maximum or a minimum? And what we see from this is that there's no extreme value here. No extreme value at x equals 4. So these three situations really lead us to what's called the first derivative test. And it basically tells us this information. If we have a critical number and the signs of the derivative, of the first derivative, change on either side of that critical number, we get a relative extreme value. If the signs don't change, we don't get an extreme value. So here's the first derivative test. Suppose x equals c is a critical number of a function. If the derivative is positive to the left of c and negative to the right of c, we get a relative maximum at c, because the function must have been increasing, then decreasing, so we get a maximum. If the derivative is negative to the left and positive to the right, then x equals c is a relative minimum, because again the function must have been decreasing first, then increasing. If the derivative has the same sign on both sides of the critical number, then the critical number is neither a maximum nor a minimum. All right, so the idea would be the function is increasing, stationary for a moment, and then increasing again, or decreasing, stationary for a moment, decreasing again. This is called the first derivative test, and we use it in conjunction with the increasing and decreasing tests that we saw earlier. So let's take another look at that function we started with in this topic, in this section. We had the function t cubed minus 15t squared plus 63t plus 3. We calculated the derivative. We found the critical numbers, right? So we saw that t equals 3 and t equals 7 were critical. We set up a number line for the derivative. 3 and 7, and it looked like this: positive, negative, positive. So, understand this again, right? So this is saying that f of t is increasing, then decreasing, then increasing. All right, so f of t, our original function, was increasing, decreasing, and then increasing again. And when when t equals 3, the derivative was 0, and when t was 7, the derivative was also 0. What is this telling us? I know that at x equals, at t equals 3, there is a relative maximum. Three is a critical number. To the left of 3, the derivative is positive. To the right of 3, the derivative is negative. Relative maximum. At t equals 7, there is a relative minimum. Seven is critical. To the left of 7, the derivative is negative. To the right of 7, the derivative is positive. Relative minimum. Now, we can be more specific though. We know that there's a relative maximum or relative minimum, but we can actually find the specific point that is a maximum or minimum. All right, so then at t equals 3, there's a relative maximum. So we can say the point 3, f of 3. Now, f of 3, so now we would have to go into the actual function. Now, the function, remember, was this thing, t cubed minus 15t squared plus 63t plus 3. We'd have to actually use that to evaluate. All right, so let's do that. I'm doing this on my handheld calculator here. I've got t cubed minus 15t squared plus 63t plus 3. All right. So if I evaluate that at 3, I get 84. So the point 3, 84 is a relative maximum. Similarly, the point 7, f of 7. All right, so then 52 2. So that's 752 is a relative minimum. So that is how we can use calculus to find relative extrema for a function. We find the critical numbers, we do our increasing decreasing test, and then we can use the information from the increasing decreasing test to tell us about the critical numbers themselves, whether they are relative maximums or minimums, just depending on the signs on either side of the critical number. Alright, so let's look at a couple more exercises. Here's one. We have q of t is 7 minus 2t plus sine 4t over the interval 0 pi. Where is where's the function increasing? Where's the function decreasing? Classify any critical numbers as relative maximums or minimums. Write the local extrema as ordered pairs. You should be able to complete this exercise using, hopefully, only a scientific calculator. Now would be a great time to pause. Try this one out on your own before I do it. Alright, so let's first note that Q is continuous on 0 pi. Right? The sine function is continuous everywhere, then the rest is polynomial, so that's fine. Let's find the critical numbers. Let's find the critical numbers. So critical numbers, let's calculate the derivative. Q prime of t would be negative 2 plus cosine 4t times 4 from the chain rule. So that's negative 2 plus 4 cosine 4t. Alright, so that's defined everywhere. It's never undefined, so let's set it equal to 0. Whereas negative 2 plus 4 cosine 4t equal to 0. Add 2, divide by 4. Cosine of 4t is 1/2. Alright, so now where is the cosine 1/2? Let's find a few of these, because remember, my interval is 0 to pi, but I've got that 4t, and so if we sort of think about the periodicity, that changes the period of the cosine function, doesn't it? We learned that back in trig. So let's see, if cosine 4t is equal to 1/2, that means then that 4t is, where's the cosine 1/2? The cosine is 1/2 at pi over 3 and at 5 pi over 3. Those would be the values on the over 0 to 2 pi. Let's find a few more just by adding 2 pi's. So let's see, that would be 7 pi over 3 and 11 pi over 3, and let's do 2 more just to be safe. So 13 pi over 3 and 17 pi over 3. Alright, and so now let's divide by 4 to actually solve for t. Alright, so then t would be pi over 12, 5 pi over 12, 7 pi over 12, 11 pi over 12, 13 pi over 12, 17 pi over 12, and, however many others. Now, we were only on 0 to pi. That's all we care about is the interval 0 to pi. So 0 to pi would go up to 11 pi over 12. So those are our critical numbers. These are the critical numbers on the interval. These are my criticals. Alright, so I've got my critical numbers. Let's run the increasing decreasing test. let's find where it's increasing, decreasing. All right, so I've got to set up my number line, and it's going to stop at 0 and at pi. And so here's pi over 12, then 5 pi over 12, then 7 pi over 12, and then 11 pi over 12. All right, so now we just need to test some values in here. And this gets a little bit tricky. It's not too bad. And I'm going to test into, I'm testing into q prime of t is -2 plus 4 cosine of 4t, right? That's the derivative that I was using. So let's just pick right in the middle of 5 pi over 12 and 7 pi over 12. Let's use 6 pi over 12, which is pi over 2. So q prime at pi over 2, that's this point right here in the middle, that would be -2 plus 4, then the cosine of 4 times pi over 2, the cosine of 2 pi is 1. And so that would be positive. All right, somewhere between 7 pi over 12 and 11 pi over 12, let's choose 9 pi over 12. I'm choosing these very carefully to make life nice, right? 9 pi over 12. 9 pi over 12 is 3 pi over 4. That's easy to work with. That's -2 plus 4 times the cosine of 4 times 3 pi over 4 is 3 pi, which would be, and the cosine of 3 pi is -1. So that's a -6, so negative. And so if you do something similar to this, you'll get, it'll turn out like, it turns out that the signs will alternate. All right, so what do we know? Classify any critical numbers as relative maximums or minimums. So pi over 12, 7 pi over 12, and will give us relative maximums. Okay, so we have relative maximums. Remember, for a maximum, we look at the critical number. It must be, and then the derivative must be positive to the left and negative to the right. So I have a relative maximum at pi over 12. I have a relative maximum at 7 pi over 12. All right, what about minimums here? I'm using that magenta highlight. Minimums, critical number, we want the derivative to be negative to the left and positive to the right. So 5 pi over 12 and 11 pi over 12. All right, now it did ask for ordered pairs, right? It says write the local extrema as ordered pairs. So here, we would have to actually use the function values. All right, so we have relative maximums at pi over 12, and then the function at pi over 12. And I'm just going to get an approximation from the calculator for this, since we've got a trig function and in combination with a polynomial. It's not going to be a nice number, so let me set up my calculator here. 7 minus 2x plus the sine of 4x. Make sure that your calculator is in the correct mode in radians, and you can do this. You don't need a graphing calculator to do this. You can do this with just a simple scientific calculator. All right, so then at pi over 12, I get 7.34 to 2 decimal places. Pi over 12 is 7.34, and we have a relative max again at 7 pi over 12. Let's see, 4.20. I have relative mins at 5 pi over 12, and then the function at 5 pi over 12. 3.52. And at 11 pi over 12, and the function value at 11 pi over 12 is 0.37. All right, so that completes that exercise. All right, so let's do one more of these. So here I'm asking you to do the same exercise with the function x squared e to the x. Find where it's increasing and decreasing. Classify any of the critical numbers as maximums, relative maximums, or minimums, and write the local extrema as ordered pairs. So now would be a good time to pause. Try this one out on your own. All right, again, we don't have any continuity concerns here. X squared times e to the x, polynomial times a basic exponential. It's defined everywhere, so I don't have any domain concerns here. Let's find the critical numbers by calculating the derivative. G prime of x would be 2x times e to the x plus x squared times e to the x. So then that's e to the x by, I'll write it as x squared plus 2x. Set that equal to 0, whereas e to the x by x squared plus 2x equal to 0. Now e to the x cannot equal 0, but x squared plus 2x, that's the same as x times x plus 2, and that can equal 0 if x is 0, x is negative 2. So we have two critical numbers. Set up our number line. Here's negative 2. Here's 0. And I'm testing into g prime of x, which is e to the x times x plus 2, right? I just used that further factored form. Recall that e to the x is always positive, so we're really only worried about the x and the x plus 2. All right, so let's check our signs on g prime of x. How about testing at negative 3? G prime at negative 3 would be positive. E to the x is positive. X would be negative 3, which is negative. Negative 3 plus 1 is negative 1, which is again negative. And so that would be a positive. Between negative 2 and 0, how about negative 1? G prime at negative 1 would be positive times a negative times a positive, which would be a negative. And finally, how about g prime at 2? That would be a positive times a positive times a positive, which is a positive. All right, so let's look at this. The derivative goes from positive to 0 to negative, right? Positive, critical, negative. That's a maximum when x is negative 2. The derivative goes from negative, critical, positive. A minimum at 0. All right, so the local extrema. G of x has a local maximum at negative 2, comma, and then g of negative 2 would be 4e to the negative second. Which you can approximate that. And a local minimum at 0, 0. Alright, so that concludes this video on the first derivative and the shape of the graph. Now later on we're going to be using these ideas in conjunction with further ideas we learned from the second derivative to actually see how to sketch curves. So it's a good idea, we need to know these techniques, but we're going to add on to them and learn some other pieces. Alright, so I hope to see you there.